So in this session we will see a special system which is called as LTI system. So it is a special case of system which we will discuss, and it is a very important for the gate point of view. Okay, so let's see. LTI system. So LTI system means it has to satisfy both linearity as well as time invariant. So it has to satisfy both linear and time invariant. Suppose if I take an LTI system, let's say what is the input output relations it can give? LTI system. Okay. Try to understand. Suppose if x of t is the input, let's assume the output is y of t. Let's assume the output is y of t. Suppose if I take k1 x of t, then what is the output for this is nothing but k1 y of t. K1 y of t. Okay. Next, if I take k2 x, if I take x of t minus t naught, then because it is a time invariant system, we have to get the output is also delayed by the same time. So that is nothing but y of t minus t naught. Suppose if I take k2 x of t minus t naught as the input, then for this the corresponding output is k2 y of t minus t naught, because homogeneity. Next, suppose if I take k1 x of t plus k2 y of k2 x of t minus t naught as the input, then what is the corresponding output we can get, which is nothing but k1 y of t plus k2 y of t minus t naught. So remember, for an LTI system, if this kind of input is given, then we are going to get this kind of output. So that's what the LTI system. So in whole, I can give for LTI system, if x of t is the input, y of t is the output, k1 x of t plus k2 x of t minus t naught is the input, then the output is k1 y of t plus k2 y of t minus t naught. Okay, take it. So this is about the linear system. So linear system is going to give you the output in this form if it is the input is in this form. Okay, take it. Let's see. The question is, the input output waveforms of LTI system are as shown in figure. The input output waveforms of an LTI system are as shown in figure. Okay. They have given input and output in this way. So this is what x of t. It is given as input for an LTI system. Then the output what it is given is zero, 1, 1, y of t. Okay. So they have given input waveform and output waveform for an LTI system. But what if the input is, if the input is in this way? then what is the output we are going to get? So what is the output if the input is like this? Okay, so try to understand. So many people will do mistake here, like they will assume that for this is nothing but the differentiation. That means if you differentiate x of t, you are going to get y of t. That's not correct. Why? Because if you differentiate this curve, you have to get the impulse at 1. But are you getting the impulse function at 1? Because there is a sudden jump from 1 to 0. There must be an impulse function which is not there. So definitely that is not the relation between them. Next. So we don't care what is the relation between x of t and y of t. But because of it is a LTI system, by using LTI system properties, we can get the output very easily. How? So first try to understand what is the input they have given. What is the relation with this with the x of t? So you have to understand what is the relation for this with this one. Okay. So let's see. Can I say input, if you observe carefully input, whatever the part here 0 to 1 which is 1, exactly x of t. And next, if you shift this x of t by 1 unit, means if you delay the x of t by 1 unit, it will comes like this. So it will comes like this. Once it comes like this, if you multiply with -3, you are going to get this one. So in simple, I can write the given input in terms of x of t is nothing but x of t minus 3x of t minus 1. 3x of t minus 1. So this is what the input. We know for x of t, if it is y of t, if the input is in this form for LTI system, what is the kind of output we are going to get? Output must be y of t minus 3y of t minus 1. So same thing, y of t we have to write exactly the same way, and we have to shift it by 1 unit and multiply with -3. So we are going to get output in the form like this. Zero, 1, 1. From 1 to 2, it is going to be -3. So this is what the output what we are going to get. Okay, take it. Impulse response. Okay. Try to understand what do you mean by the impulse response. Response, that means output. Impulse response means it is the output when the input is an impulse function. So whatever the input, that is nothing but impulse function. Suppose if the input is an impulse function, then the output, which is nothing but called as impulse response. That is as simple as that. That means suppose let's say if it is given like this, a system, let's say continuous time case, if I take, if x of t is the input, let's say y of t is the output. Let's say y of t is the output. Now, if I give x of t is equal to delta t, that means in particular, if I give the input is nothing but impulse function, then the corresponding output y of t is impulse response, and it is represented with a h of t, and it is represented with h of t. In the similar manner, if I take a discrete time system, let's assume x of n as the input, y of n as the output. If I have taken x of n is equal to delta n, then the output y of n, which is called as h of n. So remember, h of t in the continuous time case or h of n in the discrete time case are called as impulse response. Impulse response. Impulse response. That's what the impulse response. Okay. And one more thing, remember, in LTI systems, the LTI systems are represented by using the impulse response. So, in general, LTI systems are represented by impulse response. Represented by impulse response. How? Like, let's say, this is what the representation of LTI systems like by using the h of t. Suppose if it is a discrete time case, they will show it like a h of n. Okay, take it. Number 22. In the previous question, which is nothing but question number 21, I haven't given the number. Please take that. There is a question number 21. So let's see the question number 22. The unit impulse response of a discrete time LTI system is. The unit impulse response of a discrete time LTI system is. That means they have given h of n is equal to 1, 2. Arrow is here. Then obtain its output if the input is. Then obtain its output when the input is 4, 5. So they have given h of n and x of n. They want to find out what is the output of the system. Okay. First try to understand. The given system is a discrete time LTI system. Discrete time LTI. So if x of n is the input, y of n is the output. Now, what if delta n is the input? If delta n is the input for any discrete time LTI system, this is going to be h of n is the output. H of n is the output. But in this case, they have given x of n, which is 4, 5. 4, 5. Then what is the output for this? Then what is the output for this? That is what we have to find out. Okay. First try to understand. X of n, which is nothing but 4, 5. That means at n is equal to 0, its value is equal to 4. And n is equal to 1, its value is equal to 5. That's what x of n. Now, what I am doing is, can I represent x of n in terms of impulse functions? Yes. At 0, we are having an impulse function with strength is equal to 4. And at 1, we are having an impulse function delta n minus 1 with strength is equal to 5. So, we can represent this x of n like 4 delta n plus 5 delta n minus 1. We can represent it like this. Now, try to understand. For delta n, the output is h of n. If it is a LTI system, 4 delta n plus 5 delta n minus 1. For this, can you tell me what is the output if it is a LTI system? We know, just now we have seen that x of n having y of n, then k1 x of n plus k2 x of n minus 1, sorry, k2 x of n minus n naught is having the same kind of output, but just we have to replace x with a y. So here also, if I have written the input in the form of 4 delta n plus 5 delta n minus 1, what is the output for this? Which is in terms of h of n, that is 4 h of n plus 5 h of n minus 1. So we have to find out 4 h of n and 5 h of n minus 1, and we have to add them. Okay. So let's see. 4 h of n, how it look like? 4 h of n. H of n has to be multiplied with 4, that is nothing but 4, 8 Next, 5h of n minus 1. 5h of n minus 1. That means, what is h of n minus 1? If I shift this arrow left side by 1, that is 0, 1, 2. 0, 1, 2 has to be multiplied with 5. That is nothing but 0, 5, 10. So by adding them, I can get the output. By adding them, I can get the output, which is nothing but 4, 13, 10. So this is what the output for the system. Okay, take it. Next, in LTI system, one very important topic we have to discuss is nothing but the convolution. So let's try to understand the convolution. Convolution. So what do you mean by convolution? It is something like a mathematical operator, like a multiplication, addition, subtraction, like that. It is a mathematical operator. Why we have to use the convolution? Where the application comes. That means, if I say given input for LTI system, especially for LTI system, they have given input and they said this is the h of t. That means impulse response is given. So they have defined the system and they have given the input. We have to find out the output. So there the convolution comes into picture. What the convolution is? What is the operation we have to done with x of t and h of t so that we can get the output is nothing but the convolution. That means convolution of x of t input and impulse response is nothing but the output. That's as simple as that. So convolution is applicable for LTI system. So is a mathematical operator used to find the output of an LTI system. Remember, it is all about LTI systems. Of an LTI system when input and impulse response are given. Impulse response are given. That means, suppose for LTI system, if they said h of t, this is x of t, then what is the output y of t, which is nothing but x of t convolution with h of t. The convolution symbol is this one, convolution with h of t. That's what it is. Suppose if it is a discrete time system, h of n. If x of n is given as the input, then how we can calculate y of n, which is nothing but x of n convolution with h of n. X of n convolution with h of n. So remember, so to find out the output, what is the operation we have to perform between input and impulse response is nothing but the convolution. Okay, try to take it. Okay. Before try to understand the convolution, suppose a signal x of n, which is input, let's say at -1, 0, 1, let's say So this is x of n which is given. So I don't know the exactly the values at minus 1, 0, 1, 2. So can I call them at minus 1 we are having x of n which is nothing but x of minus 1. At 0 we are having the value which is x of 0. At 1 we are having the value x of 1. At 2 we are having the value x of 2. This is what the input x of n in the form of x of minus 1, x of 0 like that. Now try to understand what I am doing. Can I write x of n like at minus 1 we are having an impulse function with strength is equal to x of minus 1. So I can represent it with x of minus 1 delta n plus 1. Can I represent it like this? This line having a strength x of minus 1 at minus 1. So we know delta of n plus 1 is existing at minus 1 whose value is equal to x of minus 1 plus at 0 it is represented with x of 0 delta n plus at 1 it is represented with x of 1 delta n minus 1 plus x of 2 delta n minus 2 delta n minus 2. So this is the way we can represent x of n. In general, can I represent x of n, any signal x of n, summation k is equal to minus infinity to infinity x of k delta n minus k. Can I represent it like this? How, sir? See, try to understand. Suppose k value is changing from minus infinity to plus infinity, but in this case it is having only minus 1, 0, 1, 2. So let's say k value is equal to minus 1. What we can write? X of minus 1 delta n plus 1. Yes. If k is equal to 0, x of 0 delta n. If k is equal to 1, x of 1 delta n minus 1. If k is equal to 2, x of 2 delta n minus 2. This is the way we can represent. So in general, any signal can be represented in this form. That is nothing but x of k delta n minus k. Now try to understand. If it is the input for LTI system, what is the output for it? Okay. So let's say LTI system if delta n is the input, then what is the corresponding output, which is nothing but h of n. Because impulse is the input, we are going to get impulse response as the output, which is nothing but h of n. Suppose if I take delta n minus k as the input, then we are going to get h of n minus k, because it is a LTI system, time invariant property we can use. Next, x of k delta n minus k, then I can get x of k is a constant. So if any constant is multiplied from the homogeneity property, output is also multiplied with the same constant x of k, h of n minus k. Next, from the linearity property, if I take these kind of inputs and sum them, then output is going to be get sum x of k delta n minus k. Then output is also the same, which is nothing but summation k is equal to minus infinity to infinity x of k h of n minus k. So if you try to understand, what we have written here is nothing but the x of n. This is nothing but x of n. What we are going to get for a input is nothing but the output y of n. Output y of n. So I can say simply this is nothing but the convolution formula when if it is a discrete time system. Okay. First take down this, then we will write some more points. If the system is defined with h of n, we are talking about LTI systems only. Now, if x of n is the input, we are going to get y of n, that is nothing but x of n convolution with h of n. What is the mathematical formula for this? Which is nothing but summation dummy variable changing from minus infinity to plus infinity, x of k, that means x of dummy variable, h of n minus dummy variable, that is h of n minus k. So this is the formula for the convolution in the discrete time case. Now, what if I take continuous time case? In the continuous time case, let's see, suppose if the impulse response is h of t, if input is x of t, output is y of t, what is the relation? Which is nothing but x of t convolution with h of t, convolution with h of t. Now, try to understand. So we have to see the similarity between discrete time case and continuous time case. In the discrete time case, if it is a summation, in the continuous time case, it is going to be integration. Minus infinity to infinity. X of dummy variable, that is nothing but x of tau, h of t minus tau d tau. So this is what the convolution integral, this is what the convolution summation. Okay, take it. I haven't done any proof here, so try to understand, because it is a simply a analogy we have taken. From that analogy I have written this formula. Okay, commutative property. So we are not seeing any proofs here, so that is going to take a lot of time, but after that still we have to remember what is the result. So directly I am giving you the properties. Commutative property. So we know the commutative property. What do you mean by that? Suppose if you shuffle them, still it is going to give you the same result. That means, let's say y of t is equal to x of t convolution with h of t. That means h of t convolution with x of t. That's what the commutative property means. That means if you interchange the system and signal, it won't make any difference, because this is simply a mathematical formula. So it cannot identify which one is a signal, which one is a system. Even though if you take two signals, still it is going to give you the result, because it is simply a mathematical operator. So remember, so x of t convolution with h of t is also equal to h of t convolution with x of t. That means we can change the formulas also. We know this x of t convolution with h of t, which is integral minus infinity to infinity x of tau h of t minus tau d tau. This is also equal to h of t convolution with x of t. Then we can write integral minus infinity to infinity x of t minus tau h of tau d tau d tau. So this is the formula. In the similar manner, for a discrete time case also, y of n is equal to x of n convolution with h of n. So this is also equal to h of n convolution with x of n. H of n convolution with x of n. So here x of n convolution with h of n, this is having the formula summation k is equal to minus infinity to infinity x of k h of n minus k, h of n minus k. But if you shuffle them, this is going to give you summation k is equal to minus infinity to infinity x of n minus k h of k, h of k. So this is what is called as commutative property. Next property what we have to see is associative property. Associative property. What the associative property is saying that, suppose if you take x of t convolution with h1 of t convolution with h2 of t. So we are having two convolutions. That means we have to perform the convolution two times. So we don't have the formula for two times convolution. That means for three signals we cannot perform the convolution. That means first we have to perform the convolution between two signals, then we have to convolute with the other signal. That's what we have to do. So what the associative property is saying that you can convolute any two signals first, and convolute with the remaining signal. That's what it is saying that. That means, suppose if you convolute first x of t, h1 of t, then this whole convolution with h2 of t. Or first if you do convolution with h1 of t and h2 of t, then this whole convoluted with x of t. That also can be done. Or sometimes you can convolute with x of t and h2 of t, these two, last two. Then you can convolute with h1 of t. Because commutative property is saying that we can exchange them. So that is also can be done. So you can do convolution for any two signals first. Then you can convolute with other signal. That's what the meaning of associative property. So this is equal to x of t convolution with h1 of t whole convolution with h2 of t is equal to x of t convolution with h1 of t convolution with h2 of t. That is what it is. Okay. So what is the application of associative properties? We can find what is the overall impulse response when the systems are cascaded. So let's see, cascaded systems. Cascaded systems. That means suppose if I take a first system which is h1 of t. Next system h2 of t. Now for this system, if input is x of t, you tell me what is the output of first block, which is nothing but x of t convolution with h1 of t. This is the output of the first block. Then this is the signal for second system. That means this is the input for the second system. Then what is the output for this is nothing but x of t convolution with h1 of t whole convolution with h2 of t. From the associative property, I can rewrite this as x of t convolution with h1 of t convolution with h2 of t. That means what I am doing is, if input is given x of t, then we are getting the output is x of t convolution with something. I hope you understood what I am trying to say. So if x of t is the input, directly I am seeing the final output, which is nothing but x of t is convoluting with something. So I told you output is nothing but x of t convolution with impulse response. That means I can say this total thing h1 of t convolution with h2 of t is going to be the overall impulse response when the two systems are cascaded. That means I can replace these two systems with a single system, whose impulse response, overall impulse response, is nothing but h1 of t convolution with h2 of t. So if x of t is the input, the output is x of t convolution with h of t. So remember, from here onwards, when two systems are cascaded, then what is the overall impulse response is nothing but the convolution of the two impulse responses. Clear? Take it. Distributive property. What is the distributive property saying that? Suppose if x of t convolution with h1 of t plus h2 of t, then we can distribute it inside this bracket. What do you mean by that? X of t convolution with h1 of t plus x of t convolution with h2 of t. So this is what the output we are going to get. That means if h1 of t plus h2 of t whole convoluted with x of t, we can represent it like this. This is going to help you in finding out overall impulse response when the systems are parallel systems, parallel connection. How? Let's see. H1 of t H2 of t. For both of them, we are having the same input, and if they sum, if they get sum, this is called as parallel connection. Okay. Now you see, if input is x of t here, the same input goes to H1 of t, so that I can get the output here is x of t convolution with the H1 of t. The same input goes here, so that I can get x of t convolution with the H2 of t. H2 of t. Then, because it is a summing the signals, we are going to get x of t convolution with the H1 of t plus x of t convolution with the H2 of t. From the associative property, this is equal to x of t convolution with the H1 of t plus H2 of t. That means if the input is x of t, we are going to get output is x of t convolution with something. That something is nothing but the overall impulse response. That means I can replace these two systems with a single system which is having impulse response is sum of the two impulse responses, which is h of t is equal to h1 of t plus h2 of t. That's what we are going to get. So if input is x of t, the output is x of t convolution with h of t. Okay, take it.